Yeah, I'm Nate Oostendorp, and thanks for having me this evening. For the last couple of years, I've been working on computer vision stuff, and specifically where computer vision intersects the industrial internet and big data. And in manufacturing, they don't really call it computer vision. I'll just go with the little one then. They call it machine vision. And you can think of machine vision as being a way for a computer to understand a physical process and to really analyze a physical space. Now, machine vision's been in automation for about 30 years. Early 80s is when it kind of started getting popularized. And some factories, like for instance automotive transmission plants, now have several hundred cameras in them that are taking pictures at different steps of the assembly process for your transmission. Now, the only thing that's wrong when I look at that picture is that for all of the gigabytes of data that those cameras are capturing and analyzing, usually they send one bit back to the PLC, pass or fail. And so that is too much MapReduce in the big data parlance. We are witness to a tremendous convergence. The cost of camera sensors is dropping. The ability to process large amounts of data on cloud platforms, the ability to store massive amounts of data costing less and less every year. And also, we now have a lot of open source infrastructure that we can use to drive these tools. And this is what we need to build. The ability to take an entire manufacturing process from raw materials to finished product, take photographic record of every step in that process, align it with sensor data, align it with machine data, and put together a coherent picture of how things are made. And why this is important is that we have real constraints around manufacturing quality. It limits the complexity of what we can invent. And so you may think of quality in terms of like defects in a car, and certain primitive things may have parts per million defects, but we will soon have the ability to go to parts per trillion defects. Not defects per car or cars per defect, but defects per day in car plants. And that's due to what the industrial internet will bring. And a lot of our global problems are deeply rooted in manufacturing challenges. If you look at renewable energy, if you look at designing better batteries, if you look at making cheap solar cells, and like the picture of the Starship Enterprise, if you want to go into space, if you want to build something on the scale of the Starship Enterprise and have it run like a Swiss watch, you have to have this invention first. So the reason why is that when engineers develop a process, they have to make a lot of guesses. They can't anticipate everything. And when they actually build it, all of these little discrepancies creep in. And sometimes these discrepancies compound and they produce errors in the system, things that fall outside of a normal tolerance. And right now the way that they fix that is they make a bunch of parts, they look at the defects, they track down the root causes, they add more controls, and iterate over and over again until they think they have something which is acceptable. Back in the 1990s, I worked at a plant that did coating of what they call aspheric rear view mirrors. So rear view mirrors where the radius of the mirror changes. And we had a 10% efficiency rate in our manufacturing process. But because the glass cost $6 and the mirror cost $100, nobody cared. They just kept smashing glass and throwing away a bunch of coated toxic chemicals because it was 10% efficient. Now, soon we will have the ability not just to look at where we expect to have problems or where we know we have problems, but to monitor all of that data all of the time. Now, where does computer vision fit into this? Vision in many ways is the ultimate sensor. It produces massive amounts more data than traditional sensors. and it has some trade-offs. It's very, very hard to get a vision sensor to 99.9% accuracy when you're reading a signal versus, for instance, a prox switch. But the machine vision incumbent technology has done a great job at what I would say optimizing the specs of vision sensors. The more megapixels, the faster frame rates, the faster algorithms that run on single farmed or single crop silicon farmers. The real challenge is taking all of this data and tying it together, and that is what we're trying to do at Sight Machine. The pictures are actually mostly interesting to humans, and we save the pictures, and they're really there so that when you want to drill down and look at something, you can see them. But for computers to automatically analyze things, we need to be able to make sense of what the pictures say. And so we have to extract features from the pictures. And once you've extracted features, you've gone into what I've kind of described as a 3-step quality cycle. And for those of you who develop software, this will sound very familiar. You extract features, you put it in a statistical framework so that you can read signal from this feature data, and then you compare this to a known data sample so that you can tell how close you are to being able to read the picture. And the difference between this and what I would consider traditional computer vision is that traditional computer vision tends to be associated with bitmaps. A traditional computer vision algorithm, you handcraft that feature detector so that it gives you the perfect feature back in all of your variety of conditions. Our approach is to take lots of features, maybe inaccurate features, features that we're going to throw away. But if the signal is there and you can get it using a statistical framework, even if it's something as simple as a mean or a standard deviation, or something as complex as machine learning, like a support vector machine, you can get the signal out of there. And it's going to be a lot more robust to what are traditional machine vision problem conditions. Finally, you need to be able to label data. If you can label data and get a true set of data, then you can use very similar to the way that software developers use test-driven development to make sure that what you are changing in your machine vision test isn't just reacting to the last outlier that you got. So, we understand that machine vision, computer vision can be hard. We've tried our best to make it easier with our open source framework, SimpleCV. If you are interested in doing some computer vision, go to simplecv.org and give it a try. The factories of the future will have thousands of eyes, and they will enable us to build things that we never would have thought before possible. And let me show you a little bit of what this looks like right now. This is just the basic how it works. Cameras on a plant floor, web services in the cloud, lots of charts and graphs. If you've looked at cloud architectures, you've probably seen this slide. What may be a little bit different is that instead of data coming from servers or data coming from credit card transactions, they're coming from cameras. This is a steel annealing plant that looks at the microstructures of steel to test its hardness. The areas in red are what are considered pearlitic regions, or areas where the carbon hasn't broken down. And they have to cook the steel to a certain temperature so that these areas disperse. So we wrote an algorithm that measures dispersion. They can look at their microscopic sample of their steel and ship it on to their downstream supplier, who uses the steel to make fasteners for the automotive industry. This is a tier 1 auto supplier. They make bolts varying in size from a 1/4 inch to an inch. This was our first customer. We gave them a flatbed scanner. They destructively test samples in their batch run and cut them in half, put them on the scanner. Previously, this took about 30 minutes of operator time to do these measurements because you would have to take it to a contour tracer and an optical comparator. And now it is a single shot with the flatbed scanner, and better yet, it records the data. So all of the control charting that they do on all of their measurements is now done automatically, and they get alerts if any of their measurements fall out of control. This is something that they would never do on a regular basis. This is something that they did if they had problems or expected to have problems. The bolts get shipped to a car manufacturer. We inspect different parts of the exterior and interior parts of the car. And we can give Pareto charts and the other kind of language of statistic or of quality statistics that tells them what problems are you having, when did those occur, what shift did they occur. Another application that we've done is wheel and tire assembly. These are chicken patties that go to Subway restaurants. And all of these are visual sources of data that feed into the information that they need to make their operation run better. And ultimately, you have to realize that, we have a lot of analytics tools for computers because it's fairly easy to get the data. It's harder to get the data for these, but once you get it, you have this complete picture of an operation. And so you can do things that you never would have thought possible before. Thank you.
Thank you, Nate. We're going to take a few questions. I guess my question would be, how much customization is required to go from a car manufacturer to another factory to Subway, chicken patty? Do you need to basically build a slightly different product each time?
Yeah, there's basically 3 points of customization. One is we usually do some customization on the web interface, which, we have frameworks. This is pretty straightforward, I think, to this audience. You have to do customization of your vision algorithms and vision analytics. And then you have to do customization of your hardware. This we usually like to outsource if we can to a traditional machine vision integrator, and we just kind of pass that cost along. Our target time for the amount of effort is about 2 developer weeks. And part of our challenge as a business to scale is crunching that down by building better and better tools.
Very, very good. Questions? One over there.
Okay, my name is Jans, I'm from Canada. My question is, where is the borderline between, not so complex things and very complex things where this computer vision gives big benefit and where it's so small that it's not even efficient? Or there isn't such case, or there is?
No, I think there is. I think, though, the extremely low cost of cameras will drive that down, at least from a physical standpoint. And my hope is that the types of, kind of throw everything at the wall and winnow the data out approach to machine vision can take that out of the algorithm side. There's a lot of vision that's out there which, and the other thing is that in manufacturing, at small is very, very relative. $50,000 is small in many cases. That can be a small job, and so you've still got a lot of buffer there. But if a camera doesn't make sense, another sensor might, and that data still can be recorded. But if it's a factor, if it's something that can be variable, it really should be measured if it's going to impact things downstream.
It should be done in all cases, right?
Yeah, I mean, again, if it's going to impact something downstream, if it's something you have a tolerance around, there are a lot of cases, there are a lot of measurements, for instance, that they don't actually care about. So, for instance, the bolt manufacturer doesn't actually care about how far their bolt sticks out, because that has a tolerance of something like 5 millimeters as opposed to 50 microns on a lot of the interior geometry. And so, you obviously want to focus on the things that are going to impact how a part or how a product operates.
Thank you.
Great. Thank you very much. Turkey, thank you.
Cool. Thanks.